The Babylonians, those are the people who lived in the Middle East between the Tigris and Euphrates River, about 2,000, oh, I shouldn't say 2,000 years before the Common Era, so about 4,000 years ago. And there were a number of city states, and they became the first people who were interested in integration. Not the integration that we're learning here. This is sort of has to do with Isaac Newton and Leibniz. But their problem was this: they wanted to tax citizens fairly based on how much land they have. But the rivers in the area move, and as the rivers move, some farmers get more arable land and others get less. And you can imagine the bank of a river as being very curvy and not straight. And they didn't know how to measure the size of these plots of land. And so they were the first ones to really think about this problem of integration. Now, take a look at the graph that I've drawn in front of you. We've got this function f of x, and we want to find the area under the curve. So we want to find this area right in here. Now, the ancient Babylonians, they knew how to find the area of a rectangle, right? If I draw a rectangle off to the side here, right, and it has a height of a and a width of b, well, the area of a rectangle is just equal to a times b. So they knew that. That was easy. And one of the key insights of integration is that it actually relies on the area of a rectangle. So the Babylonians would look at this curve. So they want to find the area underneath this curve. And they would say, well, what happens if I just drop a great big rectangle in here? So I'm going to draw a rectangle all the way on the outside and all the way down like this. And we'll call this, well, we'll say this point here is A. Well, no, I'll do it like the last one. This one will be B, and this one will be A. And so they've got a rectangle here with width equal to, well, B minus A. And the height over here is FB. So the rectangle area A is equal to B minus A, or just B, times f of B. And the problem with using the rectangle, and maybe the good thing too, or the insight, was that, well, the area they wanted is here, so they got that as part of the measure, so that's good. But out here, this is like some sort of error, right? That's not part of an area under the curve, but it's going to be included in our area calculation if we use this giant rectangle. Okay, so in your head, think of it. We're trying to use this big rectangle. We capture, an area that's too big, and we've got this error term here. Now, I've gone ahead and cleared up the screen. Now, here's where the Babylonians got smart. They said, okay, the rectangle was too large. Some of the area is not actually arable land, it's river. So what if we use two? So they're going to try to use two rectangles and then add the area of each rectangle together. Now, let's suppose we cut this in half. So we've got T, and one rectangle is going to be this size. And we're going to have another rectangle that's this size. And so notice that if we use two triangles, we have an error here, but this area up here is now excluded. And that's properly excluded, right? We don't want that. That's not an area under the curve. That's not part of the area under the curve. We want the area down here. But notice that if we use two smaller rectangles, we get a more accurate result. Let's write that down. Two smaller, or the sum of two smaller rectangles is more accurate than just one larger rectangle at estimating the area underneath the curve. And so the ancient Greeks also picked up on this idea. And so if you want to measure a curvy border area, if you want to measure the area underneath a curve, you can use rectangles to estimate it. And the smaller your rectangles are and the more rectangles you use, the more accurate your result is going to be. So imagine if instead of just using 2 rectangles, what if we tried to do this with a bunch of little rectangles? So we could have a little rectangle there, another one there, another one there, another one there, and so on. And we're getting a more accurate estimate of the area under the curve. That's the intuition of integration. If you want to see a formal definition or a formal proof of how the integration works, and that it cuts those rectangles till they're really, really, really small and really, really lots of them, you can look at that in the textbook on pages 326 to 327. There's a problem with negative values for f of x. So here you can see when we evaluate f at between a and b, for that matter, f of x has a value that's less than 0. And that's a problem because there's no such thing as negative distance. The space between 2 of my fingers cannot be -2, right? It can't be -2 miles to the corner store. And that's a problem. So the distance can't be negative and area can't be negative either, because area is a function of distance. So how are we going to remedy this problem? In this conceptual way, I want to know what this area is right here, but it's a negative space. And it turns out we're going to have a very simple, very elegant solution. We're just going to flip. We're going to flip the function into positive space. And so, essentially we're just going to redefine a new function, g of x, and put a negative value in front of our original f of x function. So we're going to flip it into positive space. And you can see the instructions right down here. So we can still find the area of A, but we have to sort of imagine that it's going to be this positive space. Here's an example. We've got a function that if we're between, if we're in this area here, f of x is less than 0. So let's see if we can solve, or if we can take the integral of this thing, f of x, and find the area in this shaded spot. Now I'm going to start off by just putting a negative sign, and I'm going to have my definite integral. I want to evaluate from, let's say, let's evaluate from this point here to this point here. And so we're going to have, here we've got x is equal to 0. Here we've got x is equal to, well, since the y-axis variable is equal to 0 here, we can cheat a little bit, and we know that this function is going to be equal to 0 when x is equal to 3 log 3. And so going back to my definite integral, I'm going to have 3 log 3 at the top, and I'm going to have 0 at the bottom. So I haven't changed the limits of the integral. Now I'll write the function that we're interested in evaluating. like so. Now I'm going to integrate it, so I'll write the integral line here. 3 log 3, 0. So I'm going to integrate it, but I'm not actually going to plug in the values yet and calculate the area. I'm just going to try and integrate this thing. So if I want to integrate x over 3, I'm going to get 3 x over 3. Right? The derivative of this thing is going to be equal to e to the power of x over 3. Next, negative 3. If I integrate negative 3 with respect to dx, I get negative 3x. And I'm going to put the dx here, and then I realize that I forgot to have my minus sign. The minus sign, I didn't write it again. So now I've integrated the thing, but I still have to evaluate its limits. Now we're ready to evaluate the limits. So I'll start down here and to the left, and we're going to start with a negative sign there. I'll put a big bracket, and then I'm going to write 3e, where the x is now a 3 log 3. Sad looking 3. And over 3 minus 3 log 3. And what happens when, so this is when x is equal to the upper limit. What about the lower limit? I'm going to write a negative sign. Remember, I've got my nice bracket here, so I don't have to start changing signs yet. And I'm going to write minus 3e to the 0 over 3. So that's just going to be equal to 1, but I'll leave it like that for now. 3, 0. And I'll close the square bracket. Now I'm ready to do some simplifying, so I'll bring in the negative sign. So we're going to have 3e. Well, the 3's are going to cancel out, so we'll have log 3 up there. Well, I could simplify it more. I'll leave it like that for now. I've got a plus sign here, so I'm going to have 9 log 3. And over here, e to the 0 is 1, so I'll have minus 3 and then a 0 at the end. And make sure that that should be a plus 3. Now I've got e to the 3, so that's just going to be negative 9. The e and the log cancel out, the 3 comes down, so we have negative 3 times 3 plus 9 log 3 plus 3. And I've got negative 6 plus 9 times log 3. And now I'm going to have to turn to my trusty calculator. And I get 3.89. That's the area of this thing in here. How do I know? Do I know if it's correct or not? Well, why don't we use that old Babylonian trick? And if I wanted to find the area of that rectangle is equal to 2 times 3, which is 6. And if I drew a line from 3 to 2, then the area of that triangle, geez, I'm making an awful mess here. But if I get rid of that and I say, oh, I've got a little triangle here, if I want to find the area of this triangle, it's going to be half the area of the rectangle, and so it's going to be equal to 3. And so I found that the area is actually a little bit larger, and that makes sense because it's curvy and it's sort of bowed outwards. And so the area probably is 3.89. It seems like a very sensible solution based on looking at this now very messy graph that we have. But you can kind of see a triangle there. The area of that triangle is 3, so our answer is pretty close. Now, what do we do if we have a function that dips between positive and negative space? Sometimes f of x is larger than 0, sometimes it's less than 0. Well, we can deal with that, but you have to remember that we need to flip the curves into positive space. And so maybe the easiest way to show you this is to draw it out. So maybe I can try with put a little a here and a b there and a c there and a d there. And so if I want to find this whole area under the curve, so I want to find the area a, b plus c plus d, essentially, I'm going to evaluate this function. So a is going to be negative c1 to a f of x dx plus the area b. So the area b, that's above in positive space, so I don't need to add a negative sign. I can just go from c2 to c1, c2, c1, and f of x dx plus the c area. C is in negative space, so I'm going to have to put a negative sign in front of this integral. And then the integral is going to be c3 to c2 f of x dx. And then finally d over here. It's in positive space, so I don't need to add a negative sign. And it's going to be from b to c3 f of x dx. And so if I add up each of these 4 individual areas, I'll get the total area of the blue shaded part of the diagram. Here's one for you. Give it a try. Remember what you're doing. You've got a definite integral. So integrate this function with respect to t. And then try it yourself. Press pause. Work through it. If you get stuck or you want to check your answer, press play, and I'll show you how to solve it. All right, the first thing I want to do is I'm going to try to integrate the function. So notice that 1 over t minus 1 is equal to t minus 1 to the power of negative 1. And that looks like the special case where we're going to apply that special rule that's going to integrate us. When we integrate, it's going to give us the natural logarithm. So I'm going to get the natural log of t minus 1. The derivative of that is 1 over t minus 1 plus t squared over 2. So using the sort of the reverse power rule. Now I'm ready to evaluate this integral, and the limits are 2 to 3. So I'll start off with 3. So I'm going to have log 3 minus 1 plus 3 squared over 2 minus log t minus 1 minus 2 squared over 2. And I'm going to get log 2 plus 9 over 2 minus, well, the log of 1 minus 2. And I've got, what have we got here? we've got log 2 plus 5 over 2. Log of 1 is just equal to 0. And if I'm using a calculator, I could evaluate this at 3.193, although on an exam I would definitely give you full marks for just leaving it as it was on the previous line.